Hello everyone, today let's take a look at QP65 where we're proving some useful things about a series summation of the natural numbers basically. So in part A, we want to show that the sum of the first n natural numbers, so from 1 all the way up to n of k, is equal to n times n plus 1 divided by 2. So for example, if n was 6, well that would just be 1 plus 2 plus 3 plus 4 plus 5 all the way up to 6. So 1 plus 2 plus 3 plus 4 plus 5 and plus 6. Basically the thing to notice here is that if you pair up our first number and our last number and then you add them up, so 1 plus 6 is going to be 7. And then you take the next two, 5 plus 2 is also going to be 7, and the next two, 3 plus 4 is also going to be 7. Now all you have to do in this case is notice that we have 3 different pairs of numbers that sum up to 7, so we just have 3 times 7, right? So this is just going to be 21, and we didn't even have to add all these numbers up. Now let's do some more examples and try to find a pattern. So when n is equal to 7, again we can use the same strategy. Let's pair this number up with this one. They sum to 8. 6 and 2 sum to 8. This works because we're decreasing this one by 1, but we're just increasing this one by 1, so they're going to have the same sum. So I pair these up and they're 8, I pair these up and they're 8, I pair these up and they're also 8, but now you can see that when I have an odd number, I'm not going to have a number to pair up here when I get to the very middle. So in this case, I have 3 different pairs of numbers that add up to 8, these 3 right here. So I have 3 times 8, and then I have this one in the middle, that's just 4. So I'm just going to take 3 times 8 plus 4, and that's just going to give me 28. Now let's just do one more where n is equal to 8, and then let's find a pattern. So I take k equals 1 to 8 of k. So again, same strategy. I can pair these numbers up here. They're going to sum to 9. Same with these here, and then same with these. So I have 4 different pairs of numbers that sum to 9. So my final answer should be 4 times 9. So that's going to give me 36. So now you can see that there are 2 cases. If I have an even number here, well then I'm going to be able to pair up every single element and it's going to be easier. But if I have an odd number, well then I'm going to have one number that cannot be paired up, and it's going to be the middle element. So let's try to find the formula for our 2 different cases. Case 1, the easier one, let's say when n is even, right? You can see that I can do the same thing. I pair my first element and my last element, I get a sum of n plus 1. If I pair up this element with this element, I'm going to get n minus 1 plus 2, again a sum of n plus 1. Same with the next and the next. So when n is even, I'm going to be able to pair up every single element. That's obvious because literally the definition of being even is that you're divisible by 2. So I'm going to have n divided by 2 different pairs of elements, and then I'm going to have each of these summing up to a value of n plus 1. So it's just going to be n times n plus 1 divided by 2. Okay, ran out of space there, but this is the formula that I got when n was even. So now let's just do it when n is odd. So case 2 is going to be n is odd, and let's do it that way. When n is odd, we can still pair off the first and last elements like so, and it's still going to sum up to n plus 1, but then when I get to my middle element, I'm not going to be able to pair it up. You can pretty clearly see this middle element is just going to be the median of this sequence here, and when we have this arithmetic sequence, it's also just going to be the average. So I'm just going to take n plus 1 divided by 2. That's the value of this middle element. You can see that it works here when n was equal to 7. When n is equal to 7, well, we have n plus 1 equal to 8. 8 divided by 2 is 4, which is our middle element, right? Now I have n elements in this sequence. Obviously, I have one that didn't get paired off, so that means I'm going to have n minus 1 elements that did get paired off, so I'm going to have n minus 1 divided by 2 different pairs of elements. All of those pairs are going to sum to n plus 1, and then for my final remaining element that didn't get paired off, it's just going to be n plus 1 divided by 2. So this is going to be my formula when n is odd. Now when I simplify this equation right here, I distribute this inside here. I have n times n plus 1 minus n plus 1, and then I have a plus n plus 1, so those are just going to cancel basically, and we're just going to be left with n times n plus 1 divided by 2, which is the exact same thing that we got when n is even. So it doesn't matter if n is even or odd, we're going to have the same formula. Okay, now just quickly, this is pretty simple. Let's just prove it by induction real quick. So to show this by induction, I start with my base case. What's my base case? When n is equal to 1, this is going to be very simple. I plug in 1 over here. The sum of 1 is going to be 1 on this side. And then when I plug in 1 over here, I get 1 times 1 plus 1, so 2, and then divided by 2. So this is also going to be 1. So we have proven it for our base case. Now for my inductive step, I assume that for some m greater than or equal to 1, that this formula is true, and I need to show that it holds for n equals m plus 1. So I assume that this formula up here is true for some m. What does that mean? Well, that just means that the sum from k equals 1 to m of k is equal to m times m plus 1 divided by 2. Now I need to use this to show that it's true for m plus 1. So we know that the sum from k equals 1 to m plus 1 of k. Well, we can just break that down into the sum from k equals 1 to m plus 1. That was of k, by the way. I forgot to write that in there. But we know that this was equal to this. So this is going to be equal to m times m plus 1 divided by 2 plus m plus 1, which is just going to be 2m plus 1 divided by 2. So we can add these. And when I add these over our common denominator, obviously I'm going to get 2 plus m times m plus 1 divided by 2, and that's exactly what we wanted to show in the first place. That's just because if I plug in m and m plus 1 to this side, then I will get exactly this back. So we just showed by induction that this formula is true. Okay, now in part B, this one's going to be a little bit harder to think about intuitively. One way you can think about this, maybe because I just did the hockey stick identity, is just to notice that binomial coefficients are going to be a lot easier to think about in terms of a sum. There's going to be a lot of formulas for those. You can convert k squared to being in terms of a binomial coefficient by basically taking k choose 2. We know that's pretty close because k choose 2 is k times k minus 1 on 2. So you can see the k squared in there. And in order to isolate the k squared, what we can do is multiply this whole term here by 2, and then we can add back on a k. So something like this. That's just going to simplify, obviously, because these are going to cancel. Then we're going to have k squared minus k up here, and then we're going to add k, and these are going to cancel, and you're just going to be left with k squared, right? So that's how you think about that. So instead of k squared, which is hard to think about it, let's replace it with this. And now you can see how we might do this. Basically, this right here is going to be equal to 2 times the sum from k equals 1 to n of k choose 2. We can factor out the 2 because it's a constant, obviously, and then we're going to add on the sum from k equals 1 to n of k. We can do that because you can distribute a sum. And look, we literally just calculated this term in part A. It's going to be n times n plus 1 divided by 2. So now we just need to find the value of this term. Just because literally in my last video I did the hockey stick identity QP 135, we know what this is going to be equal to. Obviously, if we start with our iterator at k equals 1, well then 1 choose 2 doesn't make any sense, so let's just start it at 2. 1 choose 2 is just going to be 0, right? Now, pure hockey stick identity, QP 135, this is going to be equal to n plus 1 choose 3. Now all that's left to do is some algebra. I'm going to have a 2 here, so let's start with that. When I expand this term out right here, what am I going to get? Well, I'm going to get n plus 1 times n minus 1 divided by 3 factorial, which is going to be 6, right? So that was this term right here. Now I just need to add on my other term over here. Let me make some room by getting rid of this. This is just going to be plus n times n plus 1 all divided by 2. Okay, first of all, we can cancel this 2 with the 6. We're going to get a 3 down here. Now we need to find a common factor. It's going to be 6. So we're going to multiply this one by 2 right here. So when I do that, I have 2 times n plus 1 times n minus 1 divided by 6 plus this term I'm going to multiply by 3. So 3 times n plus 1 divided by 6. Now, sorry for all the algebra. All I did here was just distribute this term inside of here to get this term. Then I added these two up over my common denominator and I got this over here. When I add these two up, you can see that I'm just going to get an extra term here of n times n plus 1. Now finally, I can factor out an n times n plus 1 from this term and this term. When I do that, I'm just going to be left with n times n plus 1 times 2n plus 1, which is exactly the formula that we have up here. Now there are other ways to derive the equation for this formula. I think the hockey stick's the best. Maybe it's because I just did it, but basically another way you could think about it is that just realizing that this is probably going to be cubic in n. It's going to be some type of cubic polynomial. So we're going to have some coefficient times n cubed plus some coefficient times n squared plus some coefficient times n. I'll call it c. And then we're going to have some type of coefficient with no n term, right? It's just going to be a cubic polynomial. Then once you've guessed that this is kind of the form that it's going to look like, you can just plug in a bunch of values for n, solve some type of linear system of equations, and then you're going to get the values for all these coefficients. And when you do that, you'll get the exact same formula. Right now, just to be really thorough, let's just prove this by induction. So base case n equals 1. When I plug in 1 over here, obviously I'm going to get 1. When I plug in 1 over here, I'm going to get a 1 here, a 2 here, and I'm going to get a 3 here. So 3 times 2 times 1 is going to be 6, and then we're going to have 6 on the bottom. So this is also going to be 1. So yes, the base case is true. So now for my inductive step, I assume that this formula is true for some m greater than or equal to 1. So I assume it's true, and now I need to show that it's true for some n equal to m plus 1, right? So this should be same vibes as before. The sum from k equals 1 to m plus 1 of k squared. We know that we can break that down into the sum from k equals 1 to m of k squared plus going to be m plus 1 squared, right? Now we are assuming this formula to be true, so let's plug in this value right here for this one. Once I've plugged that in, I get this. Now we just need to show that it's going to be equal to this. So just a bunch of algebra to go. I can multiply both top and bottom by 6 to get a common denominator. Now I'm just going to skip manually doing all the algebra, but all I did here was when I added these up, I factored out an m plus 1 out front, and I'm left with this on the inside. Do some simplifying in here, this is what I get. Do some more simplifying, and I can basically add up the m and the 6m to get 7m, obviously, and then I'm going to have this plus 6 at the end as well. Let me move this over. Now to factor this, we're going to use this old method, right? I take these two, multiply them, 12m squared, then I have my middle term down here, 7m. I need to find two numbers that add up to this one and multiply to this one. So what are they? Or they're going to be 3m and 4m. Then some factor by grouping action. I'm just going to split this up into 3m and 4m, and then I had my 6 here. Let's factor these like so, actually, and then basically I'm going to be able to pull out a 2m from this one. So when I do that, it looks like this, and then in this term over here, I can just pull out a 3, and I'm also going to get m plus 2. So we're going to be able to simplify this now to 2m plus 3 times m plus 2, right? And now, boom, this is the exact equation that we were trying to prove. These are equivalent, right? Yeah, that's how you prove both of these. And these are quite useful formulas that will probably come up a lot, so they are good to know.